Okay, so maybe I will just stay around. So, good afternoon, everyone. It's a genuine, true, great pleasure to be here today. Thank you for being here, and of course, I would like to thank my long collaborator and friend Isaac for having me today. I'm also very excited about this seminar, this talk. It's my first time in South Africa, first time in Greece, obviously, and I'm excited to share some recent results we obtained. I know there are many maybe barbaric words in this title. First, Josephson Junction. I'm not sure you all know what these are. And then dual Shapiro steps, probably even worse. So I will try and walk you through these different concepts. And as Isaac said, I am an experimentalist. I am building circuits, superconducting volume circuits, and then we cool them down very low temperature. By low temperatures, I mean 10 millikelvin, so a fraction of a degree above absolute zero, because we want to observe quantum effect in this not so small, not so large circuits. And so here, this is a SEM image of one of the devices we used in this experiment. And I added the color, I mean the scale bar here, so you can get an idea of how big and how large this is. So you see, it's like maybe 100, 200 micron wide. I mean the smallest feature. So it's sub-micron features. So I will explain you all these colors. What are the blue ones? What are the red ones? I will come to that, but I just wanted to start with the device. So we kind of stay on the same page. Okay, so this being said, maybe I will do that or this. Oh yeah. So as you can hear, I am French. This is a map. This one you know. Maybe what you know less is where Grenoble is. So my lab is in Grenoble. It's in the middle of the Alps. So we are surrounded by nice mountains. The top is close to 3,000 meters. And so Grenoble is famous for mountain activities. It's also famous for physics. It's probably one of the largest physics center in France. For various reasons, but yeah, we have a very large physics department and also a lot of microelectronics industry. So sometimes it's called the French Silicon Valley. I'm not sure I agree with that, but there are a lot of, let's say, micro nanoelectronics activities, both from the academic side and also industry. So yeah, if one day you're in France or nearby, please come and visit us. I would be happy to give you a tour of the lab and maybe of the surrounding. Okay, so this is where we are. Also, I like to start my talk introducing the team, because obviously it's a team effort. These are quite complex experiments. It involves fabrication, as I said. It involves heavy cryogenics. So we cannot do everything by ourselves. I guess you probably recognize this person. So we've been working on this topic for more than 10 years with Isaac. Yeah, the fits the logo. I hope I entered the right one. Yeah, we got help from all these persons, but I would like to highlight the contribution of Samuel, Nicolas, Anas, and Jan, who are PhDs and postdocs. They are really the one, driving the experiment. So big credit to this for person. Of course, to all of the people who've made it. Okay, so superconducting quantum circuits. I guess you're aware of the Nobel Prize of last week, and this is what this is about. So we are lucky enough that Michel Devoret, John Clark, and John Martinis somehow made this seminal experiment 40 years ago. It opened really a new field of research. And 40 years ago, I was barely born, and now we can keep on building on what they discovered and make a lot of fun science. This includes quantum computing, or something that might be a quantum computer one day. I guess you heard the news from Google, IBM, all these big companies. But this is also, these circuits, they are also very interesting for quantum communication. So maybe it's not so clear here, but here you have what's called the division refrigerator. This is the thing that allows us to cool down the circuit. So you have one circuit in this deep fridge. You have another circuit over there, and in between there is some tunnel. And we can in this experiment done in Zurich, Switzerland, they could share information, basically make a bell test between two distant fridges, and investigate the communication protocol and this kind of thing. I think these circuits are also very useful for quantum simulation. Quantum sensing is also something very important these days, because these circuits work in the microwave range. And microwave, you don't know, but microwave is basically the frequency of your cell phone, the frequency of your Wi-Fi, the frequency of your microwave oven. Maybe it's less useful for physics, but at least the Wi-Fi and cell phone technology, obviously, there are big things. So if you can build better and radar as well. So if you want to do an application, if you can make better sensors, that's also very useful for many applications. So that, if I just think about these four things, you might think, okay, it's a mature field, now it's about engineering, and we should just make better devices. But today, I decided to speak more the physics aspect of it, and more like the things we don't understand. So there are many more things we don't understand. Oops. Yeah, so for example, an open question is what the ultimate limit of the coherence in this system. Because I told you, oh yeah, we can make quantum computer, quantum sensing, but these are relatively large circuits, so they will couple to the environment and they will decohere. What's the limit of that is completely an open question. You might have quasi-particle, cosmic rays, you might have material defect, all this is still being studied. Obviously, these are a solid state system. So if there are solid state physicists in the audience, they know that very soon, when you're dealing with this kind of system, you are facing the many body problem, which is maybe cool or maybe frightening to decide. But this is also something that is open. If you make very large superconducting quantum circuit, can they still be quantum? How to describe them? Because you have strong interactions. So all this is also open. And also, maybe for like quantum computing application, there is a big question, which is how to protect coherence in these imperfect systems. So maybe you heard about quantum error correction, where you encode quantum information in many physical qubits to get an effective logical qubit. But then what's the best architecture, how to do this efficiently? These are also very open academic questions, because it has to do with topology and what are the best goals and things like that. So there are also a lot of questions. And today I will discuss another open question, which is what has happened if you make these circuits, quantum circuit, high impedance. So the word impedance, I guess, for a physicist is something maybe which is not so common. I agree with that. Or maybe if you have the good electrical engineering training or you're familiar with impedances, I don't know. But what I will tell you today is a story about why this is unexplored and why this is interesting in this quantum limit. And this is what we've been having fun with over the last past 8 years with Isaac and others. So first, why is it kind of not what you would have at first? Why is it a bit exotic to have high impedance? So first, I will give you a physicist point of view. So we might phrase it this way. Nature prefers low impedance or low inductance. Why is that? So let's think about two very simple electrical dipoles, maybe the simplest one. The inductor on the left, the capacitor on the right. And if I want to give a value in Henry to this inductance, I will use this formula. So the value of the inductance is mu naught times the length of the wire divided by 2 pi. Just remember that inductance is proportional to mu naught, which is the magnetic permeability. Now, if you build the capacitance, the value of the capacitance is proportional to epsilon naught, which is the dielectric permittivity of your bed. And then you have the surface of the capacitance. Of course, the larger the capacitance, the larger the value. And you have D, which is the distance between the two arms of the capacitance. So the closer they are, the larger the capacitance, and vice versa. So far, nothing new here. Now, as I said, I will use a physicist argument, and I will call here the fine structure constant. This is something, a concept very common in electromagnetism. You can use the definition you would find next to the Maxwell equation. So it's E squared over 2 epsilon naught Hc. Fine. But you can rewrite this expression like this. And actually, the fine structure constant is the ratio between mu naught, which is linked to inductance, and epsilon naught, which is linked to a capacitance. And all this multiplied by the quantum of conductance, which is something like 7 kilos. But the interesting part is that alpha, this fine structure constant, in nature is small. It's 1%. Why is that? I don't know. God decided, maybe someone else, I don't know, but it's a small thing. And remember that this is the ratio between mu naught and epsilon naught. So if it's a small thing, it means that naturally mu naught is a small number per epsilon naught, which means that naturally inductance, the natural inductance is smaller than the natural capacitance. This is why we say sometimes that we live in a low impedance world. This is what's given by nature. And as a physicist, I would like to explore what does happen when I go to the large impedance regime, because obviously it's less explored and it's less stable. Okay, so that's the question for today. Can we build large inductance quantum circuit? The answer is obviously yes. If it were no, I would not be standing here. But more importantly is the recipe, and I will tell you how we do that. But before jumping into the experiment, I want to give you a more electrical engineering argument why having large inductance is difficult. So before you had the physicist point of view, now you will have the electrical engineer point of view. So let's say that you want to build a circuit. Yes, please.
Simply to say that why large inductance quantum circuits are important. I mean, nature prefers low impedance, right?
Yeah.
So why those?
So this is the next slide, if I may
Yeah,
answer later. In a very my physicist point of view is that anything that is unexplored is interesting. That's the two-state answer, and then I will elaborate a bit more and give you clearer points.
It's like having a big fine structure.
It's like working in a world where alpha is equal to 1.
I see.
So you have a lot of new effects. Okay, before speaking about that, I would just like to give you my simple electrical engineer argument. So let's say that you're a microwave engineer, you want to build some circuits and you want a large inductance because I don't know, for your antenna application or for your whatever application you need that. So what you do is you go online. I don't know if you use DGT or Idospares or whatever online vendors or circuits of component, and then you find a nice inductor and you want to buy it, and then you might ask yourself, okay, is it a good inductor? And what you find in the data sheet is this kind of plot. So this is impedance versus frequency. And if you remember, the impedance of an inductor is J, complex J times L times omega, right? So you see at low frequency, you do have this linear dependence. This is the L omega dependence. Here, there, here, there. But very soon, when you go to higher frequencies, you depart from this linear behavior. You have this resonance. And this is because any inductor comes with a straight capacitance. Because any piece of metal will have some, will be coupled to some ground, to some other pieces of metal, so this will give you some straight capacitance. So this is why it's difficult to build high inductance or high impedance circuit because of straight capacitance. So in the lab, this looks like this. So you have like the standard spiral inductor. You might have more advanced spiral with magnetic cores. You might have like multi-layer spiral, whatever. They all come with the same problem, parasitic capacitance. So what you want is to control this parasitic capacitance, and you want it to be low loss. Because keep in mind that you want to point circuits. So if you have any lossy component in your system, all your quantum behavior will be washed out, and you're done. I mean, you're back to a classical high impedance. So this is what we want to do. Now, coming back to your question, why is it interesting? So the first answer is, what if we were to live in a large alpha, in a large fine structure constant world? What would we find? So you would find very small footprint circuits, because if you have a huge inductance density, you can make your circuit much smaller for the same value of the inductance. So that might be interesting. This is also very much magnetic field resilient, because then you apply a magnetic field, but if the object is smaller, the effect on it is just less. Also, you might have very slow lights, because the phase velocity of light in some waveguide is 1/√LC. So L is electrons per unit length, C capacitance per unit length. So if you have a large L, you have very slow light, and very slow light means more time to interact, so you have stronger interactions. So for photonic applications, that's very, very useful. In what I will show you later, light propagates 200 times slower than in vacuum. So it's very, very slow. And like the index is 200. The refraction index N is 200 without loss. So that's very interesting application. Also, if you have large inductances, you might be able to build new devices. So there are proposal, for example, this one from Alexei Kitaev, to build some topologically protected qubits if you can have large inductances. And also today, I will focus on this part, which is what has happened when you have large phase fluctuation. So this is a bit more, I would say, an academic question. We would like to understand what's the duality between phase and charge in this circuit. So I'm just drawing this like this now without any explanation. I will explain what this means, no worries. But this is what you have to face if you live in a large alpha, in a large fine structure constant world. So in the standard world, in the natural world, let's say, the phase is a well-defined value, while charge fluctuates a lot. And since they are quantum conjugate from a mechanical point of view, if you are to build a large impedance environment, a large impedance system, it's the other way around. Charge might get localized and phase will fluctuate a lot. So all the effects you are used to, they are now not anymore existing. You have the dual effect that show up, and that's a lot of new things to explore. Does it answer the question?
I still
yes and no.
I'm somewhat convinced, but my question is that alpha basically consists of all the constants, right? I mean, universal constant, mu0, epsilon 0, E, H, and all these things. So my question is that how do you, I mean, you're trying to, modify alpha, basically all the constants in a way, by some method.
Absolutely. And you can see this also this formula. So you see, as you said, alpha is you have the charge, you have Heisenberg constant, you have speed of light in vacuum. So it sounds like it's very, there is nothing to do about it. But what you have to keep in mind is that as soon as you work inside the material, you should multiply epsilon naught by the relative epsilon, and you should also multiply the mu naught by the mu r. And this is how we do it.
Okay, fair.
And then it's like, at the end of the day, I can rewrite this, and it's like I'm changing the speed of light, if you want, because I'm not anymore in vacuum. So of course, these experiments can happen only in a solid state. If you're in vacuum, you will have alpha equal 1%, that's given.
Yeah.
So this is artificial alpha, of course. Makes it just to be very, very clear. Oops, sorry.
What is it general meaning outside a high impedance regime?
Which one, sorry?
The last slide.
Oh.
Phi q equals to E. Phase charge value.
Oh, yeah, so it means that the phase variable, that's the commutator between phase and charge variable.
Yeah, but is this equation only valid in the high impedance?
Oh, no, it's always valid.
It's always valid. So
Sorry.
what is the fluctuation? Which one fluctuates?
Exactly. So it's just Heisenberg written like this. And if you have a large charge fluctuation, you will have a localized phase and vice versa. And what I will explain, what comes next, is that phase and charge are the two element variables to describe the circuits. So like the position and momentum, if you want. So phase is the phase of the superconductor. So it's not the number, but it is the phase of the superconductor. And Q is the charge itself, the superconductor. The number of charge, if you take a piece of superconductor, you can count the number of charges. This is the charge. And since you have a macroscopic wave function, you can, this here as a macroscopic wave function, you can associate the phase to this wave function. This is the phase. And you can show that they are quantum conjugates. Or I don't know, I didn't do anything. Okay, so this is a object. So even though we are working very hard in the clean room, it's still big deal. Dirty and ugly, but
Nicolas, your skin is not visible.
So you can think about it as a sandwich between a superconductor, an insulator, and another superconductor. So you have aluminum, which is the top electrode here in white. Then you have an aluminum oxide, which is very thin dielectric, maybe 3 nanometer. And then you have bottom electrode, which is this darker electrode here. And if you cut along this dashed line here, you make a cut and you look on the edge, this is what you will see, aluminum oxide, aluminum. So you can think about it as a tunnel junction, but for couple pairs. So this is what a Josephson junction is. But as you can see, you also have two pieces of metal, two pieces of superconductor that are facing each other, so you are really forming a parallel plate capacitance. So any Josephson junction comes with its own capacitance. So this is the equivalent circuit, so the capacitance here limits the capacitance of these two facing electrodes, and this cross means the tunnel junction. The Josephson elements, the couple pair based tunnel junction. So now just some few formula. So you have what's called the first Josephson relation that relates the current flowing through the junction to the phase difference. So theta 1 and theta 2 are the phase of the two superconductors. So the macroscopic phase of superconductor 2 and the macroscopic phase of superconductor 1. And what Josephson showed in his Nobel Prize winning work is that the current flowing through junction is just given by the phase difference between the two superconductors. Yes.
The two kind of spikes at the top are those sort of manufacturing.
Oh, these guys here?
Yeah.
Oh, yes, absolutely. Because we are doing some angle evaporation to fab this. So these are like the shadows, the mask. Yeah, absolutely. We would love to get rid of that, but it's not easy. So this is the first Josephson relation. You also have a second Josephson relation that links the evolution of this phase to the applied voltage. So if you apply voltage V across your Josephson junction, V is just the derivative of time of this phase. Or if you want, the phase is the integral of the junction. So this is what Josephson predicted, and with these two relations, you can understand all the physics of this seemingly simple elements. What is now very important is that you can also associate an inductance to this Josephson element. I'm defining an inductor as a generalized inductor as the derivative of di over d phi. So maybe remember, for a standard inductor, phase is or flux is equal to L times I. So indeed, L is the di over d phi and the inverse of di over d phi. If now you have a phase, the current phase relation that is a bit more complex, which is of course the case here, you will have an inductance that is actually nonlinear, which means that the value of this inductance depends on the phase difference across the junction. It's not anymore a constant inductor. Okay, so as I said before, we have any junction comes with two electrical elements. One is the pure Josephson element, the pure tunnel element, and one is the capacitor. So now if I want to write a Hamiltonian for this thing, I will have two terms. One is called the charging energy, and it's linked to the capacitor, and one is called the Josephson energy, and it's obviously linked to the Josephson elements. So this is the form of the charging energy. You have a Q with a hat, because it's an operator now. So Q squared. This is the energy term for capacitor. And you have the cos phi. Sin phi was for the current. If you integrate it once, you get the cos. And now this is the Josephson Hamiltonian. So cos phi. Now you can think about this cos phi term as a potential energy, while you can think about this charging energy as a kinetic energy. So it's very much like a mechanical system where you have potential and kinetic energy. Okay, so if I now draw the potential, if I say, oh, this is a potential energy, I can define u of phi, versus phi, and you see I have this cosine. Okay. And now I can say, oh, my junction, I want to represent it as an effective particle. If I have a kinetic energy and a potential energy, it's fair to say that I want to think about it as just a particle moving in a potential. So the potential is this given by the cos, and then the kinetic energy will tell me how localized or how delocalized my effective particle is. If it's trapped at the bottom of the potential, or if it can escape and go across. So a very famous effect in this Josephson physics is quantized transport. So this is the basis of metrology nowadays. So this is how people define the volt. The volt standard, if you go to labs, to National Meteorological Institute, NMI, they define the volt according to the Josephson effect. And this is very important because nowadays you know that electrical power costs a lot of money. So you better have a well-defined volt, because volt is also watt. So you want to make sure you don't pay your electricity. I mean, you pay it at the right price. So it's not just a physicist problem, it's also a very, now everyday life problem. So what is the Shapiro step? So what you do is that you put a current source, in parallel with your Josephson junction, you have a resistance to add some damping, and what you will do is that if you pass some current through your Josephson junction, it's like tilting the potential, because you are flowing a current, so you like tilt the potential. And now what you do is that if you tilt a bit more, you see the particle. Oh, sorry. It is. So you see my particle is initially there, and if I increase slightly more the current, then this barrier is not high enough and the particle will jump there. Okay. So almost. Yes. Here we are, it jumps. Okay, and now if I stop, if I lower the current, it's trapped again. Okay. So now what I have to do is to tilt until at the very specific pace, at the very specific frequency. So now if I do that in the proper way, then we can write down this very simple analysis. So every delta t, so delta t is the period at which I tilt and untilt my potential. Every delta t, I jump from one minimum to another minimum. So every delta t, I jump by delta phi. Phi is this axis. And as I explained to you earlier, delta phi over delta t is a voltage. So if I do this in the proper way, with the proper frequency, I will see a voltage appearing across my Josephson junction. And what is great is that now this voltage is